Hello and welcome to the 2022 Code Jam World Finals, live from Google, New York. My name is Emma and I'm a software engineering intern on the Code Jam team. I'll be your host for today. Thanks for tuning in. Over the next hour, we'll share deep dives into the problem statements and solutions, hear an overview of today's round, and finally announce the winners of Code Jam 2022. The competition is still underway, with about 30 minutes left in the round. Good luck to all the finalists competing today. Let's kick off by hearing from Code Jam engineers. They're going to walk you through the problem statements the finalists are currently working on.
Hello everyone, my name is Selma. I'm going to walk you through the Wonderland Chase problem statement. I am a site reliability engineer in Google Cloud. On the side, I like contributing to CodeJam problem development. I reviewed the statement of this problem as a non-native English speaker, and I also developed its solution analysis. Now, let's get started. Our problem is about Alice in Wonderland being chased by the Queen of Hearts. Our goal is to identify when Alice will get caught, or maybe she won't. Alice is trapped in Wonderland Labyrinth, which looks something like this. The labyrinth consists of a number of junctions. The junctions are connected to one another by bidirectional corridors. The starting position of both Alice and the Queen are known. The Queen starts by picking her first move. Her goal is to catch Alice in the smallest number of moves. The Queen tells the Herald her move, and the Herald announces it. Alice gets to make her move before the Queen does. She now knows the Queen's next move, so she can choose the optimal move to escape it, or at least maximize the number of moves until she is caught. After the Queen moves to the announced junction, they both keep taking turns to move. They can choose to either stay at the same junction or move through a corridor to another one, until Alice gets caught, or the Queen gives up. She will do so after 1 billion moves. The goal is to know how many moves it takes before the Queen catches Alice. If they both select moves optimally, or maybe the Queen will give up and Alice will be safe. I can't wait to see some of the creative approaches our finalists take to tackle this problem. Remember, there will be a live walkthrough of the solution on the live stream after the round ends. And don't forget to check out the analysis page for the problem after the round. Goodbye.
Hi, I am Onufre, a software engineer at Google working on Google Cloud. Together with my coworker, Ulysses, we'll walk you through the problem Goose Goose Ducks.
Hi everyone, my name is Ulysses. I'm a software engineer working on YouTube. I enjoy being part of coding competitions, in the past as a competitor, and now as a contributor.
That's cool. I've also been involved in Code Jam for something like 13 years now, first as a competitor, then as an organizer, and now mostly as a problem author, in particular of this specific problem.
Awesome, so let's get started. What is Goose Goose Ducks about?
In this problem, the ducks have infiltrated the first International Geese Conference. So we have a group of participants, the geese, wandering about, and a number of pieces of evidence that we should use to identify the conspirators, the ducks among them.
Cool. What type of evidence do we have?
We have two types of evidence. First, we know the time and the place of every conspirator meeting, and we know that all the conspirators were present at every single meeting.
Okay, all the bad ducks meet here at time 5. That's simple.
Second, we have pieces of evidence provided by the participants. A participant of a conference can tell us that together with another participant, they were present at a specific time and place.
Are all these pieces of evidence true? How did Goose 1 get from one corner to another so quickly? I thought each bird covers only 1 meter of distance in 1 second.
Well, the good geese never lie, but the evil ducks can. However, we know that a duck will never contradict an earlier piece of testimony given by a goose.
So, in this case, someone lied about where Goose 1 was. Can we figure it out who it was? Well, if Goose 2 is really a good goose, then Goose 3 lied and contradicted it. But you just said that can happen. So, we know Goose 2 is actually an evil duck.
Yes, exactly. Note that Goose 3 might also be a duck, and we have no idea where Goose 1 was at any specific place in time, but we do know that Goose 2 is secretly a duck in disguise.
And so Goose 2 needed to get to the meeting place from time 6. So Goose 2 couldn't have been where Goose 1 claims it saw it at time 5, right? So Goose 1 is also a duck.
Right.
But what about Goose 3? We don't know. It could have told the truth about Goose 1. Goose 3 could be a good goose or an evil duck. What should I do?
Well, the problem asks you to return the smallest possible non-empty set of ducks.
So in this case, that's 2. Awesome. I look forward to seeing how the finalists solve the problem.
Me too. Remember to try out this and all the other finals problems on the Google CodeJam site, g.co/codejam. Thank you for watching.
Hello there, I'm Han Sheng. I'm a software engineer at Google, and I work on the Google Silicon Simulation Tools team in Taiwan. Today, I'm going to introduce the problem slide parade from the CodeJam 2022 World Finals. I had experience as a contestant in CodeJam before I joined Google, and now it feels really different as a contributor. This year, I contributed as the problem author of Slide Parade, and I also provided some ideas on generating part of the extreme test cases. Now, let's start to talk through the problem statement. In this problem, we continue the story of the company Goody, which you may be familiar with from past CodeJam problems. 6 years ago, Goody built some one-way slides to connect their buildings. Each slide allows employees to go from its origin building to its destination building. In this example, we have 3 buildings and 6 slides. Each pair of buildings has 2 slides connecting them in both directions. For example, starting from building 1, you can go to building 2. After being given the layout of the Goody campus, we are asked to design a parade using the slides. However, there are some constraints on the parade. The parade must begin and end at building 1. The parade must pass through all the buildings the same number of times. Visiting building 1 at the beginning and the end of the parade are counted only once. The parade must use each slide at least once. Currently, the parade is not valid. It doesn't go back to building 1, and the numbers of visits to the buildings are not equal. Moreover, 5 of the slides remain unused in the parade. To make it valid, we could continue the parade and go through the buildings counterclockwise and clockwise. Now the parade begins and ends at building 1, passes through all buildings twice, and uses all of the slides, so it is a valid parade. Now let's look at another layout. In this example, it's impossible to design a valid parade because after leaving building 1, say to building 2, it's impossible to go back to building 1 or go to building 3. So the 2 slides on the right can never be used. And the number of visits between building 2 and building 3 will never be equal. That's all for the problem statement. I'm excited to see the creative approaches to this problem from our finalists. After the round ends, you can try out this and our other final problems on the CodeJam website in practice mode. Stay tuned because there's still more to our live stream to come. Bye.
Hi there, I am Anusha. I am a software engineer at Google and I work for the Google Assistant Communications team out of the Mountain View office in California in the US.
Hello, my name is Bartosz and I have been a software developer at Google in beautiful Waterloo, Canada for almost 2 years. I currently work with the Display Ads Experiments team and the Google Kickstart team, which is organizing another coding competition run by Google.
Bartosz and I are going to talk about the problem Schrodinger and Pavlov for CodeJam 2022's World Finals.
We both have experience as contestants in coding competitions like CodeJam and Kickstart, and we are very excited to be on the other side, setting up challenges for all of you.
It is 1935, and a meeting between two Nobel Prize winners is producing extraordinary results. Schrodinger, a famous physicist, invites Pavlov, a famous physiologist, to see his experiments with cats in boxes. Pavlov brought his dog with him to keep up with his own research, and the combination proved interesting, to say the least. Let's start out with what the problem is asking for. We are given n boxes in a row. Schrodinger's cats may be present in some of them. Each box is only big enough to hold a single cat. The boxes are connected by a series of one-way tunnels. Each box is the starting point of exactly one tunnel, but can be the destination of 0, 1, or multiple tunnels.
The cats can move in one direction from one box to another if a tunnel exists between them. Note here that the cat can only move if the destination box is empty, as boxes are not big enough for more than one cat. Cats are usually mellow and calm and prefer to rest inside their boxes if nothing alarms them.
Pavlov's dog walks past the boxes from 1 to n and barks at each box in turn. If a cat is present in the box, it tries to escape through the tunnel, leaving that box. Note that the cat cannot use the tunnel if the destination is already occupied by some other cat.
Let us take a look at the example. Here we have 4 boxes, and we have a cat in the first, second, and fourth box. There are tunnels from the first box to the second one, from the second box to the third one, from the third box to the first one, and from the fourth box to the third one.
Now let's consider the dog running from left to right. When the dog approaches the first box, it startles the cat inside, which tries to escape to the second box. However, as the box is already occupied, it cannot go there. Then the dog approaches the second box and startles the cat inside this box. The cat escapes through the second tunnel and ends up in the third box, which was free. Now the dog approaches the third box, which is currently occupied by the cat that escaped from the second box. The cat gets startled again, but is unable to escape as the first box is already occupied. Finally, the dog reaches the last box. The cat inside this box is startled as well and tries to escape, but is not able to, as the third box is already occupied.
The objective of this problem is to predict if the last box contains a cat when the dog finishes running past all the boxes and reaches the last one. In this example, we can see that the last box will contain a cat in the end. But that's not the whole problem. In pure Schrodinger's cat tradition, we are not certain whether some boxes contain a cat or not. If we have k unknown boxes, then we have 2 to the power of k hypothetical situations, and we want to consider for all of these situations if a cat would be left in the last box. The output of the problem should be the number of ways that would result in a cat being in the last box. You need to write a program that can give an answer to all situations up to 5,000 boxes. It is common for CodeGem problems to deal with large numbers up to thousands or millions of digits long. That is easier in some programming languages than others, so to keep things fair, we often only require giving the value modulo a large prime, such as billion plus 7.
There is also an easier version of this problem that you can solve. In this version, we have at most 100 boxes and all the tunnels connect to nearby boxes. The farthest connected one can be 5 boxes away.
We are going to stop here to avoid any spoilers. We can't wait to see some creative approaches our finalists take to tackle this problem.
Stay tuned after the contest ends to see a full walkthrough of the solution, and make sure to check out the analysis page for the solution after the round ends. Goodbye!
Hi everyone, I'm Max. One of the things I work on is preparing and test solving problems for Google CodeJam. I'm going to describe the problem triangles from the CodeJam 2022 World Finals. When writing most CodeJam problems, we come up with an interesting programming problem and then invent a fun story around the problem itself. This time, we didn't write a story and just stuck with a geometry problem because geometry is fun enough as it is. So here it is. The program must read from its input a set of points in 2 dimensions. Then, the program needs to figure out a way to join up as many of those points as possible into triangles while satisfying certain rules. The triangles cannot cross each other. Any two triangles must be either outside of each other or one must be wholly inside the other, except that the vertices of a triangle can touch the edge of another triangle. For example, these configurations are okay, but these are not. The input set of points could be very large, so a program would be too slow if it tried every possible way to divide up the points into sets of 3 to make triangles. So we need another method which can solve this quickly even for a large number of points. If you want to try this problem on your own, head to g.co/codejam after the round ends, where you can read all of our previous competition problems and submit solutions to get feedback from our judging system. And make sure to stay tuned, because once the round ends, someone from the CodeJam team will walk through the solution on the live stream. Good luck to everyone competing.
It's so cool to hear about the problems the finalists are working on today. There are just a few minutes left in the competition. I can't wait to see what happens. We're going to take a short break to finalize the round, and we'll be back soon at 17:05 UTC. Stay tuned. Welcome back. The round has ended and our team is currently finalizing the results. While we wait, members of the CodeJam team, including some problem authors, will give a high-level overview of solutions to each of the problems the finalists faced today. Melissa is going to kick us off with the first problem, Wonderland Chase. Melissa, over to you.
Thank you, Emma. Okay, my name is Melissa Halsband. I work as a software engineer in the Google office in Dublin, Ireland. We're going to be going over the Wonderland Chase problem, so let's get into it. So this problem can be represented quite easily as a graph, where the junctions are represented as nodes and the corridors are represented as edges. The first thing to observe, quite trivially, is that the only way that the queen has any hope of catching Alice is that they are both in the same connected component. If they are not, then Alice can just sit comfortably and watch YouTube, and then she will never be caught. So for the rest of the problem, we're going to consider that we're going to assume the queen and Alice are in the same connected component, and we're only going to look at this component for the rest of the problem. So an important observation to make now is that Alice will be always safe if she can get into a cycle within the graph. This is because even if the queen is in the same cycle and just next to her, Alice can always go the opposite way. Sorry. And sort of run in circles, Tom and Jerry style, and at the end of the chase, Alice will be tired, but certainly safe. So we're going to be using this later on. How are we going to solve the problem now? So something we can do is we're going to partition this graph into two subgraphs. A node is going to be considered to be in Alice's subgraph if Alice can get there first, meaning that she has a shorter distance from wherever she is, and if a node is at the same distance from Alice and the queen, or the queen is closer, then this node is going to be considered in the queen's subgraph. We can find this out by performing a breadth first search and just tagging the nodes with the distance from each of these ladies, like this, and so on and so forth. We actually can use the same traversal to find the connected components if we're interested in. Okay, once we have done this, we can look at Alice's subgraph. So obviously for each node we compare the distances, and whichever is smaller we assign. And then we can look at Alice's subgraph on its own, and we can ask, are there any cycles in it? We can check this by performing now a depth first search in Alice's subgraph, or just by counting the nodes and edges. If there are as many edges as there are nodes or more, it means that there is at least one cycle, because this is a simple graph. Okay, if this is the case, then again, Alice is safe, because as we have seen, if she can get into a cycle, she can stay there and be safe. So the second thing to observe is we need to check how many edges are there that have one end on the queen and one end on Alice's subgraphs. So something like this. So if there are these two nodes that connect the two subgraphs, what we can observe is that there will be then at least one cycle that contains both the queen's and Alice's nodes, because Alice's subgraph is connected. It connects the two ends, and the same happens for the queen, and therefore we have now a cycle. If this happens, Alice is again safe, because she can reach any of the points in her subgraph before the queen can, so she can go to any part of her subgraph, and therefore she can get to any node in this loop, in this cycle that we found. Okay, so the last case to consider is if there are no cycles in Alice's subtree, and if there are no more than one edge that connect the two graphs. In this case, actually the things get a bit spicier for Alice, because the queen has this strategy of getting into her end of this bridge node that connects the two graphs. And while Alice can get into any node into her graph, into her subgraph, by definition, because she has a shorter distance, then she will not be able to get into any of the queens, because if that was the case, she would cross paths with the queen. And now Alice is effectively trapped in her own tree, because the queen is sitting at the root of a graph that has no cycle, so this is a tree. And at each step, the queen will be closing into Alice for going to whatever branch where Alice is, and eventually Alice will be caught. So what can Alice do in order to maximize the chase, and in the hope that the queen tires and gives up the chase? She would have to go to the furthest away leaf in her subtree. And which is this leaf? Well, we have calculated this already when we calculated the distance from the queen to each of the nodes in the graph. So we know which will be the furthest that the queen would have to traverse in order to corner Alice into a leaf. So this is what Alice would have to do in order to maximize the chase. And this number would have to be multiplied by 2, because both Alice and the queen take turns, and that's the result of the problem. I hope you have enjoyed it as much as I did. And back to you, Emma. Thank you.
Thanks, Melissa. Now over to Samiksha, who is going to explain an approach to Goose Goose Ducks.
Hey, I'm Samiksha. I'm from Kickstart team, and I will walk you through the problem Goose Goose Ducks. The key in this problem is to carefully look out for all the rules of consistency and then derive implications from it. We have two main information which is given to us in the problem statement. First is set of meeting points for all the ducks that were present in the conference room, and second, and also note that all the ducks attended every meeting in this list. Second, we have a list of statements that were given by birds, both maybe a goose or maybe a duck, of where they were and with whom they were. And all this is in a space-time point. So now let's take one bird in the conference room. Let's say, name it as A. Now we construct a path for A. And how do we construct it? It's like we check out all the statements that involves A, and also we take into consideration all the meeting points. Now let's say here we have P1, P2 and P3. Now we want to check if it was possible for A to go from P1 to P2, because remember that we also have a max speed limit in the problem statement. Now the another observation is that we would only look at the consecutive points for A, and that we can do it in the logarithmic complexity for this particular part of the problem. Now let's say, once we computed the speed, and let's say it's not under the limit, then we have three cases. Yeah, the first case is when both P1 and P2, the consecutive ones, they both came from meeting points. That's not possible given the constraints in the problem statement. Second, we can have like one is coming from a meeting and the another is coming from a statement. I will explain about it later, but let's also check out what's the third case. The third case is when both of them are statements. Now if we go back and remember the problem statement, we have certain rules. One is like goose would never lie, and a duck would always try to be consistent with what the goose has said before it has recorded a statement. So here, based on that, if we have the second case, then this implies that if A is a duck, then B is also a duck. And in the second case, and in the third case, it's a case that we know for sure that it's a forced duck. One thing to check out here is like how we will decide which one is the forced duck. So we will look at who claimed the PI or PI plus 1. For that, we will check the ordering of the statements of when it was recorded. Note that this is different from what we were following till now. We were following the ordering of time of traveling in the conference room. So let's say if PI was recorded first, then the claimer of PI is a forced duck. Now, once we get the forced duck, we would have to remove it, and again, we have to check the new adjacents. So in case of forced ducks, since the problem says to find out the minimum size set, our work is done. We would output the number of forced ducks we were able to find. Otherwise, what we would do, we will model our knowledge into a graph whose vertices are birds and the edges are implications. And what are these implications? Like if I say if there's an edge between A and B, then if A is a duck, then B is also a duck. So we will have these edges, and then the problem reduces into finding the smallest, strongest connected component in this graph, and note that this strongest connected component should be a final one. Yep. And for more details, you can go to the analysis of this problem. You can refer that, and thank you.
It's so awesome to hear these solutions to the problems. Next, let's tackle slide parade with Timothy.
Thanks, Emma. Hi, everyone. I'm Timothy from the coding competitions team here at Google. I'm going to explain a solution to slide parade. So we've been tasked with finding a parade route that goes through every single slide at least once, but goes through every single building the same number of times. One way we can approach this is by representing this as a graph. So the nodes will be our buildings and the edges will be our slides. If we split each node into two versions of the nodes, we can have our edges, the slides, going from one side to the other. Now, we can find a matching in this graph. This matching here would represent the slides going from 1 to 2, 2 to 3, and 3 to 1. So what this will be is a bunch of possibly disjoint cycles where we've gone through every single node or exactly one time, but we might not have used every single slide. For example, we didn't use the slide from 2 to 1. So we can actually find another matching. We can this time force the edge from 2 to 1, and then we just remove the edges that we used from 3 to 1 and from 2 to 3 and find another matching. And now this matching will be a bunch of potentially disjoint cycles where we again have went through every single node exactly one time. Now, we might not be able to find that matching, or we have to keep going for every single edge that we haven't used yet, and we might not be able to find one of them. If we don't find one of them, that just means that the parade route doesn't exist, so we can just return impossible as our answer. But if we do find them all, we now have a bunch of sets of cycles that cover our graph. And every single one of these sets of cycles goes through every single node exactly one time. And together, all of these sets use every single slide. As long as our graph was connected and we found all of these matchings, we can actually use that to build an Eulerian circuit. One thing we need to be careful with to make sure this runs fast enough is when we find the secondary matchings, we can reuse some of the work we already did from our earlier matching, so we only really have to match one more additional node instead of rebuilding the entire matching. But that's all for now.
Next is my favorite problem so far, Schrodinger and Pavlov. Yashri, take it away.
Thanks, Emma. Hello, everyone. This is Mohammed Yasri. I'm a software engineer in search team in search ranking. I'm also part of CodeJam coding competition team. Right now, we will walk through Schrodinger and Pavlov's solution. So if we are, as a quick recap for Schrodinger and Pavlov, we have a row of n boxes. These boxes contain the cat. Some boxes contain a cat, some boxes don't contain any cat, and some boxes may or may not contain the cat. So if boxes with 1 contains a cat, boxes with 0 doesn't contain a cat, boxes with question mark may or may not contain the cat. And our objective here is to compute how many configurations lead to a cat in the last box after the whole process. The process goes from left to right, from box number 1 to box number n, and at each step, if the box contains a cat right now, it can move through a tunnel to the next box, only if the next box is empty. And of course, we see that depending on the uncertain boxes, the boxes that may or may not contain a cat, it can change the number of final configurations, our solution. So for example, if we have the number of empty boxes, the uncertain boxes is k, so we have final configurations with a total of 2 to the power of k. So for test set 1, we have two special limits. So the first limit is the number of boxes is up to 100. And also the tunnels has a limit. So a box, let's say we have box number I, it can only go, the tunnel can only go to any box within a distance of 5. So I plus 5 or I minus 5, any box in this distance. It can't go to any box further than this distance. With all of this in mind, for test set 1 we can have a dynamic programming solution. This solution has this state. So the current box we are at right now and the state of the previous 5 boxes and also the state of the current boxes, the current box. And the state of the next 5 boxes. And why is that? Because we only move 5 steps, at most 5 steps ahead or 5 steps previous. And what the DB tries to compute is what is the number of configurations that will end up if we are at this box right now, and the previous 5 boxes were at this state, and the current state is this state, and the next 5 boxes are currently at this state. And of course, this dimension is up to 100, this dimension, and the second dimension is up to 2 power 5, and the third dimension is only 2 states. The last dimension is also 2 to the power 5. So the DB state is a total of 100 times 2 to the power of 11, or n times 2 to the power of 11. So we go simulate the process from box number 1 to box number n. If the box contains a cat, we try to move it if the next box is empty. And of course, if the next box is a maybe, so it can contain a cat or maybe it's empty, we branch the condition. We try if it's contain a cat, and if we try if it doesn't contain a cat. And also if the current box is a maybe box, then we also branch. So we try twice. We try if it does contain a cat and if it doesn't contain a cat. And doing so, at the end, we will count the number of configurations that end up with a cat at the very last box. This is fast enough to pass test set 1. With further analysis, we can get rid of the exponential factor. For the full details, you can check out the full analysis on g.co/codejam. That's it for now. Thank you.
Thanks, Yashri. Last but certainly not least, Pablo is going to walk us through one way to solve triangles.
Well, thanks, Emma. Hi, everybody. I'm Pablo. I'm an engineer in the CodeJam team, and I wrote the triangles problem. And I'm going to talk through some details about its solution. So in this problem, we have a bunch of points that we want to join into triangles. And we want those triangles to fulfill some definition given in the statement. So in order to solve the problem, what I'm going to do is I'm going to constructively prove a theorem. That's important. And then that construction, then we're going to make it efficient enough so that our algorithm can actually perform it in time. So here's the theorem. The idea is that in a set of 3 t points, we can make exactly t triangles, so basically use up every point, if at most 2t of them are collinear. So the direction from top to bottom is kind of immediate, because if we have more than 2t collinear points, by the Pigeon principle, at least 3 of them are going to end up in the same triangle and then not make a valid triangle. By direction in the other side is not. So let's look at it. So first, let's start with the case where there's the set of collinear points not really saturated. It's kind of far from the maximum. So let's say there's at most 2t minus 2 collinear points. So in this case, our strategy is going to be find any triangle that doesn't interfere with anything else, because since these points are all collinear, we cannot grab more than 2 of them for a body triangle, so any triangle is going to be okay because it's going to keep the number of collinear points small enough. So the way to do this is, let's say we have lots of points, right? We're going to find 2 extreme points. There's multiple ways of doing this. One is the convex hull, but the easiest way is just to sort by x and then by y and take the 2 most extreme points. So in this case, this would be these 2 points, right? So we pick these 2 points, and now we want to find ourselves a third point, and we're going to keep the triangle we pick in a different plane than everything else. So that way we ensure it doesn't interfere with anything that happens later. So because these are the 2 extreme points in this order, we know that there's not going to be anything on this side of the line. There could be some things on the line, but that doesn't really matter too much. So the way to do this is like we rotate from here like this, and we find the first point by angle, right? Because we already know that there's nothing on this side, so as we move like this, there's going to be nothing, nothing, nothing until the first point, right? So we're guaranteed that above this line there's going to be nothing there. So we could try this triangle. Of course, this in particular doesn't work because there could be a point here. But in this case, we can try from the other side. So we rotate this, and then we find this point. And then this triangle will work because this line also has nothing towards this side. The reason the second one worked is because all the points, and the first one didn't, is because all the points are below the line that joins our first 2 chosen points. So we need the direction. We don't need to check which is the right direction. Ideally, we can just like go towards both sides and just keep the one that works. If both of them work, that's fine. We pick either one. Okay, in this way, we get rid of one triangle. We maintain the hypothesis, so we just have a smaller set to solve. Now for the other case. So let's say we have at least 2t minus 1 collinears, right? So in this case, if it's 2t collinears, we want like every triangle is going to have 2 points from the collinear set and 1 point from something else. If it's 2t minus 1, there's going to be 2 points from the collinear set and 1 point from the other points in all but the last triangle, or all but one triangle. Okay, so let's do that. So let's say we have this big set of collinear points, right? We have 3, 6, 9 here. Let's say 10. And then we have 5 other points. So let's say 3 here and 2 here, right? So this is exactly 2t. So what we're going to do is going to split the 2 sides of the line. And since we have 3, 6, we want to pair them with 6 collinear points, and we're going to pick like the top 6. So 1, 2, 3, 4, 5, 6. So we're going to pair this up, and then pair this up. And then again, because these 2 planes are separated by a line, triangles here and triangles here are not going to interfere with each other, so we can just solve that separately. If there's 2t minus 1, one of these is going to have 1 fewer point. So now let's see how to solve one of these where all points are on one side of the line. So we can do something very similar as we did in the first stage. If we have all the points on one line, and some more points all here, because we pick the first 2 points in the collinear set, so the highest 2 in this case, and because we know there's nothing here, we can start rotating our imaginary line until we find the first point, and then we're guaranteed there's nothing above. So this triangle here is in this plane, everything else in this plane, so this triangle doesn't interfere with any other triangle. And we can keep doing that. So we do that, we remove this, then we pick these 2, we rotate again. Let's say we find this triangle. Notice that if there's many points that are tied by angle, we want to pick the closest one, right? Because we can like slightly skew the line so that there's still a separation line between the 2 planes. Okay, so we can be going until we have very few points. So let's say we get to 4 points, which is going to be the case if we had exactly 2t to start with. So if we have 4, then we have 2 others here. It's going to be fine because we are going to just find this triangle and this triangle. It's going to be okay. However, if we had only 3, we can run into a problem because that means we also have 3 points not on the line. And if we just find any triangle using 2 from the line, it's possible that the other 3 end up being collinear. So for this particular case in which we end up with 3, we need to do something else. Since we only have 6 points, we can brute force it. Just try every possible combination and see what works. It's not hard to convince oneself by cases, which I'm not going to do now, that every case with 6 points in which not more than 3 of them are collinear is possible to build into 2 triangles. The hardest one is when you have 3 sets of 3 collinear points like this. And we can solve this case with like one big triangle and another smaller triangle inside. The other cases are somewhat similar. And this solves the problem and proves the theorem. However, we also need to implement this somewhat efficiently. Taking triangles out in the first phase, or in the phase where we're processing the collinears, takes linear times, which is quadratic overall, which is OK. But the first phase can be slow if we keep recomputing the largest collinear set, because as we take triangles in a greedy way, the largest collinear set might change. So there's a couple of ways of dealing with that. One is to compute all the collinear sets at the same time and keep them updated in a sort of priority queue, but that can be very slow, even though complexity-wise seems efficient. Another way is to only recompute the largest collinear set when we know it might have changed. It only means recomputing in logarithmic number of times, but again, both of these approaches add some logarithmic factors and some large constants and are going to be too slow. So the easiest way to deal with it is to just ignore the largest collinear set at the beginning and keep doing the greedy step in which we just find triangles. So we find one triangle, then we find another triangle, then we find another triangle. And at some point, if we can't do it, so if we try both directions and neither works, that means that every remaining point is collinear. So at this point, we can just undo some of the latest triangles that we built until this is a saturated case, and we go straight to phase 2. So with this improvement, which is also simpler than the others I mentioned to implement, it's a little bit more clever, you can do quadratic time overall, and it's very fast. And the implementation is not that tricky. So that's it for the solution. Thank you for watching, and back to Emma.
Thanks to all of our presenters for taking us through some potential solutions and approaches to the 2022 CodeJam World Finals problems. It was interesting to see how different folks tackled each of the problems. Now, the moment we've been waiting for. Here to give an overview of today's round and share the final results are Max, Pablo, and Timothy.
Hi everyone, I'm Max. I'm excited to be here today to recap the final round, which just concluded. The finalists have worked hard over multiple rounds of CodeJam challenges to make it to the World Finals. At the beginning of the season, around 33,000 people submitted a solution in the qualification round. From there, after multiple rounds and 27 problems, it has been narrowed down to just 26 finalists from 12 countries around the globe. A big thank you to everyone who participated in CodeJam this year. And a huge congratulations to the finalists. Making it to the World Finals is a massive accomplishment. For 6 of our 26 finalists, this is their first CodeJam World Finals. It's very cool to see some new faces. 20 of the finalists competing today have made it to the CodeJam World Finals before. Welcome back. Among these returning finalists, we have 2 previous CodeJam champions competing this year, AC Rush TC and Gennady Korotkovich. The most popular coding language we saw in the final round this year was C++. The only other language used in the finals was Rust. Couchy Sheep had the first points on the board at 10 minutes and 54 seconds with a submission for Wonderland Chase. Behind the scenes, we had 35 Googlers travel to New York to work on the competition that you just watched. It's been fun to see how the round unfolded. That's all from me. Now, Pablo and Timothy will reveal the final scoreboard and announce our winners.
Thank you, Max, for all those interesting facts. That was definitely an exciting contest, right, Timothy?
Oh, absolutely. It's been so much fun, and it's time to finally reveal the final scoreboard and our 2022 champion. Pablo, do you want to explain how this works?
Yeah, of course. So what we're seeing now is the scoreboard as everyone could see it at the end of the contest, which is the scoreboard with only the visible test sets showing. So all those green check marks that we're seeing is the visible test sets that contestants solved, and they and everyone else already knows it was correct, and they got points for it, which we can see here on the right of the screen. And then the dashes are things that everyone already knows were incorrect, so no points for that. And the question marks are the things that we're going to be revealing right now. So those question marks, we're going to be highlighting them and turning them into a green check mark if that submission was correct, and giving them points, which may make them move up on the rankings, or if they were unfortunately incorrect, we're going to see them turn into a dash and no points will change. So why don't we try revealing one?
Of course. So we have a submission for Wonderland Chase from Nyan Nyan. Did they get test set 2 correct? Yes, they did, so they move up. Big Bag, did they get test set 2 correct of Wonderland Chase? They did indeed. What about Kalinin N? Did they get test set 2 of Slide Parade? No, they didn't. What about I'm Bar D? They have a submission to Wonderland Chase as well. Did they get that correct? Yes, they did. They move up. What about Dayseen? Did they get test set 2 correct of Slide Parade? No, they didn't. But what about Triangles? No, they didn't. And now, Pablo, it's kind of important to note, even the contestants that submitted these solutions don't know if the hidden test sets are correct, right?
Yeah, right. That's why we call it hidden, and that's why we're revealing them now to everyone and also to the contestants themselves.
Okay, great. So let's keep going. Did Lumabons get test set 2 correct of Wonderland Chase? Yes, they did. They move up, and they still have a submission to Slide Parade as well. What about Zeman for Wonderland Chase? Did they get test set 2? Yes, they did. What about YOLO Swag? Did they get test set 2 of Wonderland Chase? They did. They move up as well. Utaka, what about them? They have 3 test set 2 submissions. Wonderland Chase, yes, they move up potentially into first place because they still have submissions for Slide Parade and Schrodinger and Pavlov. Golovanov, did they get test set 2 correct of Wonderland Chase? They did. They move up. Mola Mola, they did as well. MHQ, they did as well, all the way up into potential first place. Now we go to MNBV Mar. Did they get test set 2 of Wonderland Chase? They did. What about QWERTY? They did as well. Simon Lindholm? They did. Wow, Pablo, it seems like a lot of people are getting test set 2 of Wonderland Chase. Was this one of the easier problems that we've had recently?
Yeah, it was definitely the easiest problem in this contest. That's why we gave it the least points. And also, we saw a lot of people trying it first, so that means they had more time and they could finish not in a rush. When the last submissions, it's more likely that you're going to make a mistake because you don't have that much time to, check it out and test it correctly because the contest is finishing.
Yeah, that makes a lot of sense. Well, we do have a lot more submissions to get through. What about Couchy Sheep? Did they get Wonderland Chase test set 2? They did. They move up as well. Zhongli, they have submissions to 4 of the problems. Did they get test set 2 of Wonderland Chase? They did. They move up into a potential first place, and they still have ones for Goose Goose Ducks, Slide Parade, and Schrodinger and Pavlov. Umnik, did they get Wonderland Chase? They did. I'm Bar D. Well, they have a submission to Schrodinger and Pavlov. We haven't seen a correct for that one yet. They got that all the way up into first place. What about Radawoosh? Did they get test set 2 of Wonderland Chase? They did. They move up. Lumabons, Slide Parade test set 2. We haven't seen a fully correct to test set 2 of Slide Parades yet. Oh, they did not. Well, what about Zeman? Did they get this? No, they didn't either. Okay, we go to XLL. Did they get Wonderland Chase test set 2? They did. They move up as well. Snook? They did as well. Okay, Gennady. He actually won 7 years in a row, but last year he was not our champion. Can he get test set 2 of Wonderland Chase and maybe solve some more to regain his place as our CoJam champion? He does get Wonderland Chase. We'll have to get back to him to see the other submissions. What about Eknarwala? Did he get test set 2 of Wonderland Chase? He did. He moves up. AC Rush, does he get Wonderland Chase? He does. What about K-Sun? He does as well. Okay, we have Ben Q. Oh, he moves all the way up. Okay, now the only submissions left are for Goose Goose Ducks, Slide Parade, Schrodinger and Pavlov, and Triangles. Pablo, out of those problems, which one was your favorite this year?
I don't know. I guess it depends on the point of view. I really like Goose Goose Ducks, and we spent quite a bit of time working on exactly how to explain it because it has some tricky details to it. But I really like how we rounded it up. So.
Absolutely. That one's really funny. I think the story for Schrodinger and Pavlov is actually super funny as well. Let's see. Does Slide Parade test set 2 from YOLO Swag, is that correct? It's not. But what about Schrodinger and Pavlov? Yes, they move all the way up into a potential first place. Now we have Utaka. Do they get test set 2 of Slide Parade? They do. They move up. Golovanov? Yes, they get that for slide parade. Okay, Mola Mola, we have a submission for Goose Goose Ducks. This would be our first correct solution to Goose Goose Ducks. They do not get that. But what about slide parade? No. MHQ, maybe they can get Goose Goose Ducks fully solved. No, they don't. What about slide parade? Yes, they move up. Okay, MNBV Mar, do they get slide parade test set 2? They do, they move up. Okay, QWERTY, they do not. Maybe Schrodinger and Pavlov? No. But will they get triangles? No, they don't. Okay, Simon Lindholm, do they get test set 2 of slide parade? No. Schrodinger and Pavlov? No. Maybe triangles though? No. Okay, Couchy Sheep, do they get test set 2 of Goose Goose Ducks? No. Maybe slide parade or Schrodinger and Pavlov? Yes, they do. They move up into a potential first place finish. Okay, Xiang Li, do they get test set 2 of Goose Goose Ducks? They do. That's actually the first correct solution for Goose Goose Ducks we've seen. That puts them in a potential first place finish because they still have submissions for slide parade and Schrodinger and Pavlov. Unique, yes, they also get Goose Goose Ducks. Radawoosh, no. But slide parade, yes, they move up. Okay, XLL, no, they don't get Goose Goose Ducks. Do they get slide parade? Yes, they do, and they move up. Snook, do they get Goose Goose Ducks? Yes, they do. Okay, Gennady, yes, he does as well. Eknerwala, no. Slide parade, yes, he moves up. Okay, AC Rush TC, does he get Goose Goose Ducks? No. No. Schrodinger and Pavlov maybe? No. Okay, what about triangles? No, he doesn't. Okay, K-Sun, does he get Goose Goose Ducks fully solved? No. But he does get slide parade, so that moves him up also into a first place potential finish. Ben Q, does he get Goose Goose Ducks? He does, he moves up. Okay, Yutaka, does he get Schrodinger and Pavlov test set 2? No. Golovanov? Yes, he gets that and moves up. Okay, MNBV Mar, Schrodinger and Pavlov test set 2? Yes, he moves up. Xiang Li, slide parade? Yes, he moves up and he still has a submission that hasn't been revealed for Schrodinger and Pavlov. Unique? Yes, he gets slide parade. Radawoosh? No, he doesn't get Schrodinger and Pavlov test set 2. Okay, this brings us to XLL. Schrodinger and Pavlov test set 2, not correct. What about triangles? No. Okay, so that brings us to our top 10. Most of these competitors actually have the potential to finish in first place, depending how the results are revealed. Does Snook get test set 2 of slide parade? He does. Pablo, we've had a lot of some correct solutions to slide parade, and this is a pretty hard problem.
Yeah, it's hard, but there's also like multiple ways of solving it, which I think makes more people able to get there. You don't have to get into the exact right path. That's just unique. I also want to point out that there's lots of these competitors that we still have to reveal that already got a lot of things correct and nothing incorrect so far.
Wow, that's very impressive. I'm sure Gennady wants to know, did he get test set 2 correct of slide parade? Yes, he did. He moves up for a potential first place finish. Eknerwala, did he get Schrodinger and Pavlov? He did. He moves up also for a potential first place finish. K-Sun 48, yes, he gets Schrodinger and Pavlov. This is exciting so far. Okay, Ben Q, slide parade, yes, he moves up as well. Xiang Li, yes, moves up all the way into first place. Unique, does he get test set 2 of Schrodinger and Pavlov? No, he doesn't. Okay, we go to Snook. Does he get test set 2 of Schrodinger and Pavlov? No, he doesn't. What about triangles? No, not quite yet. Okay, we have Gennady, who previously was our reigning champion. Can he maybe regain his title this year? Yes, he gets Schrodinger and Pavlov test set 2 correct. Well, now it leaves it up to the other contestants. If they get test set 2 of Schrodinger and Pavlov or test set 2 of triangles, they can actually overtake Gennady. Does Ben Q get test set 2 of Schrodinger and Pavlov? No, he doesn't. But does he get triangles? Ah, no, he doesn't. Pablo, we haven't seen a correct solution to triangles this year. Why do you think that might be?
Well, it was a very challenging problem. It was worth the most points together with Schrodinger and Pavlov. And like geometry, I think scares people, even the finalists, as good as they are. So they probably think, even if they think they can solve it, maybe it costs them more time than some other problems. So that's a better investment.
But some of these contestants are very good, and we have 4 more submissions to reveal. Does MNBV Mar get triangles test set 2 correct? This would bring them into first place potentially. No, they don't. What about Eknerwala? Do they get triangles test set 2 correct? No, they don't. Okay, K-Sun, can they do it? If they get test set 2 of triangles correct, they have a chance to be our CodeJam 2022 champion. If not, they will finish in 3rd place. No, they don't get that correct. So that gives K-Sun 48 the bronze medal for 3rd place of CodeJam 2022. Zhang Li is 2nd place, and Gennady Koraktovich will be our 2022 CodeJam champion.
That's amazing.
But we have one more attempt to reveal. Did Gennady Koraktovich solve test set 2 of triangles? Has this ever happened before? Have we ever had a contestant solve all of the problems in CodeJam?
No, that has never happened. I do remember a few times being in this position, like revealing the last one and that potentially making someone do it, but it has never happened before.
Well, there's a first time for everything. Maybe it will happen now. Does Gennady get test set 2 of triangles? No, he did not get test set 2 of triangles. The judges are still undefeated. Congratulations to all of our winners, finalists, and everyone who participated in CodeJam this year. We're glad that so many of you enjoyed competing, and we hope you all had as much fun as we did.
Yeah, and we are already looking forward to 2023 when we'll have our 20th anniversary season, and we hope to see all of you join us for that. Goodbye.